And the convex function, so we have seen the convex set, and convex function is basically, again, defined similar to the convex set. So a function from Rn to the R is convex if basically in the domain for any combination of x and y, this equation here is satisfied. So let me draw underline. So in this case, the combination of theta, where the theta is between 0 and 1, so in any combination of theta x and 1 minus theta y, the function, the value at this function should be smaller or equal than its independent combination, theta fx plus 1 minus theta fy. So in this case, applying fx operation first, then multiplying by theta and 1 minus theta gives a higher value than basically applying the theta first and then taking its value in the f function. So if the theta is basically doesn't equal to 0 and 1, and it's called strictly convex if satisfied for theta is greater than 0 and less than 1, and it's called convex if it's satisfied that theta is smaller or equal than 0 and it's smaller than 1. And again, if basically f becomes concave, if minus f is convex. So negation of a convex function is concave, is a concave function. And this implies from the definition here. And again, there are certain functions that are neither convex nor concave. So a function doesn't need to be either convex or concave. So, but convex functions will be quite important in optimization because as we described, convex functions or the optimization with the convex functions lead to a global optimal solution in the optimization. Okay, convex functions are affine. So one convex function is affine combination where you have this ax plus b in Rn. So if you have a single variable, ax plus b is convex, and the powers of absolute value, where p is basically greater or equal than 1, is also convex. And the powers where power is greater than 1 or smaller than 0 is in basically R plus plus, where the positive real sets is convex, positive real number set is convex. Exponentiation function where e to the power ax on real set is basically convex. And negative entropy. So entropy is basically, if you remember, so it was minus s minus x log x, or for different p's, it was p in the probability space, p times log p for multivariate variables, where p was equal in the probability space. This was the entropy, and in this case, this is concave, and its negative entropy is convex. So in this case, x log x on R on the power square. And since logarithm is defined for real positive real numbers, this is also defined in the positive real numbers. And concave function is basically, again, affine function is both convex and concave. So in this case, a linear combination is basically either concave or convex. So powers where basically p is between 0 and 1, this is concave, and logarithm is also concave. However, negative logarithm is basically convex. So these are examples on real space, and in Rn, there are more examples. In Rn, again, affine functions are convex, where we basically x is n times 1 vector. X is n times 1 vector, and A transpose x plus b is both concave and convex on Rn. And norms are convex on Rn. So in this case, the norm should be basically greater than 1. So for instance, x1, the first norm, and the second vector norm, as well as the infinity norm, which is the maximum value in basically the vector, are all convex. on Rn. And quadratic functions, such as x transpose px plus 2qtx plus r. So this is a quadratic function, and quadratic expression comes from this x transpose px. In this case, this is only convex if p is a positive semi-definite, if and only if. So if if basically it satisfies both sides, if p is positive semi-definite, this expression is basically convex. And if this expression is convex, p is positive semi-definite. So p should be positive semi-definite, meaning that x transpose px for any x should be greater or equal than 0. And this is quite important for optimization functions or optimization problems with quadratic functions. If the matrix is positive semi-definite, that will give us a convex expression, and which can be optimally solved then. And again, geometric mean is concave on a positive number space. And there is a thing called log sum expression, which is exponentiation of summations, logarithms. So in this case, logarithm, this is a parenthesis, or exponentiation of expressions is convex on Rn. And this is also convex. And quadratic over linear is also convex. So in this case, for instance, basically x squared divided by y is positive, and x squared is basically, in this case, becomes positive as well. And x squared y here is a quadratic over linear expression, and that's also a convex function. Okay, so in this case, examples of R and N. So again, there are certain examples here, like affine functions in R and N is also both convex and concave, similar to Rn and R. And logarithmic determinant function is also concave. And maximum eigenvalue function is convex. And again, there are certain parts you can try to prove. And for detailed proofs, you can look at the books of Convex Optimization by Stephen Boyd, which is in the references in the course syllabus. And again, restriction of a line. Let's look at first and second order conditions. So in this case, we have this, in order to understand the convexity, we need to, I'm skipping some part of the slides, and we need to understand first and second order condition. So for first order condition, we look at the gradient of the function. So gradient is basically, as you remember from the calculus, it's basically functions, basically first derivative with respect to the x1 and up to the n. And it's basically a vector in n space. And another thing is the Hessian matrix. And Hessian belongs to the Rn times n, which belongs to the matrix. So for each ij entry, so it's the second derivative of fx with respect to x, with respect to the xi, and with respect to the j. So here is derivative with respect to the xi and with respect to the derivative xj. And this matrix is symmetric because derivative of fx with respect to the xi and then xj is same as its derivative with respect to the xj and then xi. So this matrix is symmetric matrix. Hessian matrix is a symmetric matrix. And again, gradient and Hessian is also used in the Taylor series expansion. So for instance, fx plus, here is this expression, is equal to fx plus gradient plus 1 plus 2, and it's the Hessian in this expression with some error terms. So these are the error terms here. So this will be by using the original Taylor expression, this will be the third order terms. But here we are only expanding in terms of the gradient and the Hessian. So this is the quadratic term. in which case we are using the Hessian matrix, quadratic term in this case, and this is a linear term, in which case we are using the gradient. And the function itself at x point x. So this is its Taylor expansion around x point, around point x. So again, the Hessian results in a matrix, symmetric matrix of a derivative of f function with respect to every pair of points. And for instance, for the diagonal entries, it will be double derivative. So for instance, ith entry, which is the ith diagonal in the entry, which will be derivative of fx with respect to xi 2 times. So double derivative. Whereas in gradient, we have only single derivative with respect to the variables. Okay, so in this case, we continue with the first and second order conditions and quadratic functions. The first order condition is f is differentiable with convex domain is convex if and only if this condition is satisfied. So fy minus fx is gradient should be greater than gradient times y minus x. So this is the first order condition. So in order f to be a differentiable function, f to be convex, so in this case, fy minus fx, just a sec, let me write again. So in this case, fy minus fx should be greater or equal than basically Hessian matrix times y minus x. So this satisfies the convexity of f function, convex, if this condition is satisfied. So first order approximation becomes if a global underestimator, and second order condition is basically the Hessian matrix should be greater or equal than 0. So the Hessian matrix should be positive semi-definite. So there are two conditions for convexity, first order condition and second order condition. The first order condition is fi minus fx should be greater than Hessian transpose times y minus x. And probably you have seen this in your calculus classes. And the second order is basically f should be twice differentiable. And because we need to take the definition twice, and its Hessian matrix should be greater or equal than 0, which means that it should be positive semi-definite. Positive semi-definite. Positive semi-definite. This is the second order condition. And again, let's look at some of the examples. So for instance, here is a quadratic function. So in quadratic function, basically the Hessian is basically px plus q. So when you take this square, it becomes 2 comes down and it becomes px times q, and which is basically, this is basically the case. And since p is, and in the second case is basically a quadratic function, is the Hessian matrix is basically p itself when we take one more derivative. And since in this case, if p is positive semi-definite matrix, then this function is basically a quadratic convex function. And least square objective is always convex, because in this case, we have ax minus b second norm square. So again, this is ax b transpose ax minus b. And again, if we take its basically gradient and Hessian, we get the expressions like this. It's basically Hessian is like this. and it's basically, its gradient is like this, and its Hessian is 2 times A transpose A. And in A transpose A, this is always greater or equal than 0. It's guaranteed to be greater or equal than 0. Because in this case, the proof is, assume that we have X transpose. We have, in order to show that it's positive semi-definite, we need to prove that for any vector X, X transpose times the matrix A transpose A times X should be greater or equal than 0. So in this case, basically, this is also written as AX transpose times AX. If you know that the transpose makes the X before. And in this case, it's basically square of the vector AX, which is always positive. So that's why the least square objective is always convex. And quadratic over linear, like x squared divided by y. And if we take its Hessian, then this Hessian is basically convex or positive semi-definite matrix when y is greater than 0. And again, there are some operations, again, preserve the convexity. So non-negative weighted sum for any convex function is convex. So for example, if we have f1 and f2 that are convex, alpha 1 and alpha 2 is also convex. So if f is convex, then basically a fine transformation of the function where f of ax plus b is also convex. And pointwise maximum operation, if they have n f functions that are convex, then maximum of these function, a function that's the maximum of all of them, is also convex. So these are the convex combination. And in terms of the references, so you can take a look at the chapter 3 of Stephen Boyd. So again, the topic is right now, I haven't started in the finance part yet. I'm still going over the prerequisites or some introduction to the course. So if you are more interested in this introduction, you can take a look at the chapter 3 of this Stephen Boyd's basically course.